Hello, now we're going to finally look at some subgroups of the symmetric group. So remember, the symmetric group consists of all permutations of a set. So the first natural option, so throughout these lectures, n is just going to be a positive integer. So fix a positive integer. Consider the cycle whose elements are 1, 2, 3, 4 in order. Let H be the cyclic subgroup generated by the cycle. So this cycle sends 2 to 3, 3 to 4, ... and it sends n to 1. You can check that this cyclic subgroup has order n. So for instance, let's set n equal to 4. Then my cycle is a 4 cycle. And what is c squared? Well, 1 goes to 3. Skip counting by 2. 3 goes to 4, goes back to 1, so 3 goes back to 1. Skip counting by 2s because I'm squaring. 2 goes to 3, goes to 4, so 2 goes to 4. So there's c squared. C cubed, I'm skip counting by 3s then. 1 goes 1, 2, 3, so 1 goes to 4. Starting at 4, 1, 2, 3, 4 goes to 3. Starting at 3, 1, 2, 3, 3 goes to 2. So there's c cubed, and c to the 4th is, skip counting by 4s, starting at 1, 1, 2, 3, 4, 1 goes to 1. And you can check that 2 goes to 2, 3 goes to 3, and 4 goes to 4. That's the identity element. So you see you have order 4. In general, of course, a n cycle has order n because, well, given any element on that cycle, it has to go n places to the right before it gets back to where it started. So you have to go to the nth power in order to get the skip counting argument to tell you that you get 1 to be a fixed point. Right, because how do you compute the kth power of a cycle? You take an element on the cycle and you count k steps to the right. And so the nth element power says count n steps to the right, and if you have an n cycle, that means you're going to end up where you started. So the nth power of an n cycle fixes every element. And so you can see that an n cycle has order n. Which is kind of convenient because we call this a cyclic group and we call this a cycle, so the terminology is consistent. All right, let's pick a more interesting group. It turns out the dihedral group, the symmetries of a regular polygon on n vertices, is also a permutation group. So we're going to label our vertices. Instead of using positive integers, I'm going to use 0. And yes, I know the textbook would label this 1 through 6. You'll understand why I prefer using 0 eventually. It makes some of the calculations a little easier to understand. But let's label it 0 to n minus 1. Every symmetry of the polygon sends vertices to vertices. So every symmetry is going to permute the vertex set. It's a bijection on the set of vertices. Ergo, every symmetry is a permutation. So the collection of symmetries is a collection of permutations. And so you can prove it is a subgroup of the symmetric group. Same here. I'll give that formal proof later, but first let's actually get our mind around what these permutations look like. So first, let's start with the hexagon as an example. We'll let R be the clockwise rotation. And so when you rotate clockwise, I should have probably drawn the picture first. 0 ends up over here, 1 ends up next to it, in the clockwise direction, and you end up with that picture. And so 0 got sent to the 1 position, so 0 goes to 1, 1 goes to 2, and so on and so forth, and we get a cycle. And so then what is r squared? Well, skip counting by 2, 0 goes to skip counting by 2, 0 goes to 2. 2 to the right from 2 is 4. 2 to the right from 4 is back to 0. Wait, yeah. That isn't everything, so we close off that cycle. We still need to look at 1. Skip counting by 2, 1, 2, 3, 1 goes to 3. Skip counting by 2 from 3, 3, 4, 5, 3 goes to 5, 5, 0, 1, we close off. So there's r squared. And you can check if you rotate twice, 0 does go to 2, which goes to 4. This triangle permutes among itself, and this triangle permutes among itself. R cubed is a 180-degree rotation, so we should see 0 go to 3. If we skip count by 3s, 0 does go to 3, and vice versa. Similarly, 1 does go to 4, and 2 does go to 5. Looking at this skip counting idea. 1, skip count by 3, you go to 4. Skip count by 3 again, you go back to 1. Similarly, 2, skip count by 3, you go to 5. Skip count by 3, you get back to 2. I often found when I was a student, the best way I could do this skip counting was to actually write it as a polygon and do it that way. That allowed me to keep track of how to go back to the beginning. R to the 4th and r to the 5th. Well, we already know r to the 5th is actually just counterclockwise rotation in the end. So 0 just goes to 5, which goes to 4, which goes to 3, which goes to 2, which goes to 1. And similarly, r to the 4th is r squared negative. It's counterclockwise rotation twice. So 0 goes to 4, goes to 2. 1 goes to 5, goes to 3. Or you could skip count by 4s. Or you could use the fact that this is order 6, so r to the 4th is the inverse of r squared. And so these cycles are inverses of these cycles. And similarly, r to the 5th is the inverse of r, and so this cycle is the inverse to that cycle. All right, so that's half the group. We still have the other half to go. So here is this reflection, which I'm going to call S. It's going to fix 0 and 3. Quickly regretting not doing the square instead, but and it's going to swap 5 and 1 and 4 and 2. All right, so there's one of the reflections. Now you can start to see what the other types of reflections do. Another type of reflection fixes diagonals 1 and 4. And then it swaps 0 and 2. And 3 and 5. And then another reflection across the diagonal here fixes 2 and 5. And it swaps 1 and 3. And 0 and 4. Of course, those aren't the only types of diagonals. There's also diagonals across opposite edges that bisect the edge that we have to take into account. Namely, there's this diagonal that swaps 0 and 1, 2 and 5, and 3 and 4. A diagonal, vertical diagonal that swaps 1 and 2, 0 and 3, 4 and 5, and finally this last diagonal which swaps 2 and 3, 1 and 4, and 0 and 5. And notice I forgot the identity element, which is r to the 6th. And so there's the 12 elements in this dihedral group. And we see that they are all, in fact, permutations. As another example, let's look at n equals 5. Here I'm going to do the calculations a lot more quickly. I just want to point out that the rotation group is that 5-cycle group we talked about earlier. So we've already done this calculation. R to the 4th is the inverse calculation. So then I just need to look at r squared. R squared sends 0 to 2. In fact, you can actually trace r squared. R squared is the star. It's going to send 0 to 2, 2 to 4, 4 to 1, 1 to 3, 3 to 0. And then r cubed is the inverse of that. The hard one are the reflections. So each reflection is going to consist of fixing one vertex and its opposite edge, and then permuting the opposite pairs of vertices that we see. So the reflection fixing 0 is that permutation. The reflection fixing 1 has to swap 0 and 2, and 3 and 4. The reflection fixing 2, there's a reflection fixing 3, and there's a reflection fixing 4. So reflection fixing 2 swaps 1 and 3, and 0 and 4. At some point I need a different color. The reflection fixing 3 swaps 2 and 4, and 0 and 1. And finally, the reflection fixing 4 has to swap 1 and 2, and 0 and 3. So what I mean by fixing, I mean that there's a line of symmetry that goes through that vertex and the opposite edge. And so note that the difference is when n is odd, the lines of symmetry must go through a vertex and an opposite edge. But when n is even, you had lines of symmetry that went through opposite vertices, and then lines of symmetry that went through opposite edges. And you can see this. In this example, the reflections consisted of one cycle and a bunch of 2 cycles. And when n was even, you either had 2 1 cycles and a bunch of 2 cycles, or just a bunch of 2 cycles. So doing these examples tells you some general patterns about the way this group structure looks.